Hey there, my name is Sagar Bhatani, and I attended the extra credit physics lecture, The Physics of Baseball, by Dr. Alan Nathan on Thursday, April 4th. When Dr. Alan Nathan began his presentation, the first thing he talked about was baseball aerodynamics. He talked about how the trajectory of a ball and air resistance really plays an important part of where the ball will go after it's hit. He also talked about the Magnus force and how that opposes gravitational force. Secondly, he went into knuckleball research. He talked about the spin of the knuckleball, and honestly, he talked about his curiosity about the knuckleball and how little we know about it. Finally, he closed off with baseball bat collision. He talked about how the sweet spot of the bat really determines how far a ball will travel, and how that sometimes the batter doesn't even need to hold on to the bat in order to determine in order to have a good hit on the baseball. It's all about the vibrations of the bat. I found this lecture really interesting because I love baseball, and I thought that the physics behind it was just a cool application of science and physics in general, how we can apply physics to pretty much anything. So first off, something I didn't know in this lecture that Dr. Allen was talking about was how trajectory has such an effect from the air resistance. So when you're talking about trajectory, there's two things that you really need to focus on. It's the air resistance and the Magnus force. So the Magnus force acts positive for the baseball. Essentially, it reacts against gravity. The air resistance, however, pushes away the baseball. It's in terms of negative when we look at it. So the first thing I'd like to talk about when looking at air resistance is just how curious that topic is in general. If you look at this graph right here, you can see how this ball that was hit at an initial velocity of 100 miles per hour and a launch angle of 29 degrees with a backspin of 2,500 RPM, it was hit 397 feet, taking into account air resistance. However, when you look at when it would be in a vacuum, therefore taking away air resistance and Magnus force, it would have gone 174 feet farther at 571 feet. So we take these values and we compare them to each other, and then we get a scalar value called R. And R is pretty much an application value that we can use to compare different fields and how far different fields and such as Wrigley, Turner, other things, and find out their different R's and find out the best field to hit home runs at. Essentially, the value with the highest R will have the highest carrying distance and will be best for hitting home runs. This value was really explored with a new Yankee Stadium that was built in 2008. A lot of people call this stadium the carry away stadium, just because home runs were hit so frequently in the stadium. I found this really interesting, and I had no idea that different fields, different air densities. So something that I did know that was represented in the lecture was that the knuckleball is one of the most mysterious and random pitches of all time. Pitchers like Tim Wakefield and R.A. Dickey have made careers off this random pitch and have had relatively low ERAs throughout their careers based on this pitch. So first off, you'll notice that the knuckleball has none to very little spin. And this leads to a very small Magnus force. That means the force that's opposing gravity is minimal. Therefore, the ball kind of floats and flutters and whatnot, whatever you call it. Also, you'll notice that the direction and the magnitude is different for each pitch. So let's take a look at a pitch by R.A. Dickey. So in this clip, you'll notice that R.A. Dickey is throwing a knuckleball. And you'll notice that the trajectory is random based on the catcher's effect. He has no idea where it's even going. And neither does the hitter. So as the ball flies, you'll notice that the magnitude and the direction are random, and thus it'll lead to a random trajectory. Something that really caught my curiosity was the sweet spot of the bat. So essentially there's a spot on the bat where if you hit it, it'll be the best point to hit it. The reason that is because it has the lowest vibrational point. So there's somewhere in the middle of the bat where if you hit it, based on the conservation of energy, the most energy will be transferred from the bat to the ball, resulting in the ball traveling its furthest distance as well as its furthest maximum altitude. So something that really caught my interest in the lecture was the Todd Frazier's no-hands home run. So we can take a look at the clip right now as I'm speaking. So you'll notice that in this clip that Todd Frazier's hands come off the bat, or at least in very loose contact with the bat, as he hits the ball. So a reason for this is that and he still hits a home run in this act. The reason for this is because the impact of the ball is focused on the barrel. Therefore, the grip on the handle is actually has little to non-importance at all. So therefore, since the impact is with the barrel and the main sweet spot is with the barrel, the rebounding of the ball is also with the barrel. Through this, we can find out that the handle of the bat is actually just a free pivot. So it actually move any way, have any kind of grip, and we could still hit a home run just as long as the barrel has minimal vibration and energy is conserved. Finally, to follow up on this, I looked to follow up on the lecture. I looked into the physics of a softball, and although I couldn't find many comparisons on the softball to baseball spin ratio, I noticed that the spin of a softball actually starts in the pitcher's hand. Also, a softball can have up to a spin of 1500 RPM. I saw this on Rod Cross's website, was a recommendation off Alan Nathan's website. But yeah, the lecture was really fantastic. I really learned a lot from it. I look forward to looking up more things that are physics related and sports related as I venture through Georgia Tech in these next 4 years. Thanks, and my name is Sagar Patani again. Have a great one.